Okay, this is the recording for Thursday evening's homework, and this is an extension of what we were talking about for um, as far as physical and chemical properties and how to identify the characteristics of things and physical and chemical changes and how to identify what is happening. Those physical and chemical changes can help you determine what a substance is. So first of all, we'll start with pure substance and its definition. A pure substance is something that is built from atoms, and it cannot be broken down into anything that is simpler than what it is and keep the properties of that original substance. Elements and compounds are both considered pure substances. So if you look at the picture here, you've got, for example, helium atoms. So you've got 5 helium atoms there, a bunch of helium atoms. If you pulled out the smallest piece of helium, it would look identical to every other piece there. That is why you call an element a pure substance. If you look at the oxygen molecules, you cannot pull anything out other than oxygen. So that is why it's a pure substance. It's kind of like pure water. When you're talking about pure water, that means that water is the only component. There's nothing else there. So when you're looking at the compound water that you see in the picture to the right, it's made up of hydrogens and oxygens. So on this picture, we can identify these. So the two, you've got H2O for water. So here you have 2 hydrogens and 1 oxygen. 2 hydrogens, 1 oxygen, and same thing here. So as long as it is pure water, no matter what you pull out of there, it's always going to be 1 part oxygen, 2 part hydrogens. It's always going to be H2O. So when we're talking about a pure substance, we're talking about the fact that if you break it down to the most basic part of it, then, and it's still retaining the original properties of that substance, then it's all made up of the same thing. Pure substances always made up of the same thing. You can't pull anything else out of it. Again, like pure water or pure gold. There's nothing else that is inside of that. All right, now, when we're talking about something like when we're talking about something about like elements, this is the most basic pure substance, or we can call it the purest substance that it is, or that there is. So all of the individual atoms in an element look alike. The elements are always located on the periodic table and represented by chemical symbols. Some examples of common elements are gold, hydrogen, and oxygen. So if you look at the picture here, it tells you an element is a substance that's made up of only one type of atom. So when you're looking at copper and you were to take a microscopic view of copper, all you would find inside that are copper atoms. Carbon, going to find inside of that carbon atoms. Helium, inside there you're going to find helium atoms. So elements are, in the most basic form, they are considered the purest substance. Compounds have 2 or more elements that are chemically combined in a fixed proportion. So when we say chemically combined, we have to think back to what we were talking about as far as chemical change. If they're chemically combined, it's going to change the elements into something new and different. So therefore, compounds will have different properties from the elements that make them up. And compounds can be represented by chemical formulas that show the fixed proportion that is inside a compound. So when you're talking about fixed proportion, that means that water is always 2 parts hydrogen, 1 part oxygen. So inside every water molecule, you've got 2 hydrogen atoms, 1 oxygen atom. If that changes, like for example, if you have 2 parts hydrogen, 2 parts oxygen, that's no longer water, it's hydrogen peroxide. So every compound has its own distinct fixed proportion. So down here for your example, salt has 1 part sodium and 1 chlorine. Water, again, 2 parts hydrogen, 1 part oxygen. So when you're looking at the picture to the right, it says a compound is a substance produced when 2 or more elements combine in a chemical reaction. A chemical reaction is the same thing as a chemical change. So when water is formed, hydrogen had to come together, react with oxygen to produce water. So your chemical reaction looks like this. Hydrogen reacts with oxygen, produces water. Okay? Now, hydrogen is a flammable gas. It was in the Hindenburg. It's why the Hindenburg exploded. Oxygen is a flammable gas, but together they come together to make water, which is a liquid that's not flammable. Okay? Carbon dioxide, you've got carbon that reacts with oxygen to produce carbon dioxide. So carbon itself is kind of like the soot you would find inside a fireplace. Oxygen is inside the air we breathe. It's part of it's what we need for life. Comes together, makes carbon dioxide. That's the bubbles that come out of drinks. That's the exhaust that comes out of cars. That's the air that we breathe out. So very different. So these are chemical reactions that have happened. So a chemical reaction has to happen in order for a compound to be made. So here, a compound is always made up of 2 or more different types of atoms. All right, so how does that vary for mixtures? Mixtures is when we're talking about substances that are coming together but not chemically combined. And we call that being physically combined. And because the substances are physically combined, each substance is going to be able to keep its own, most of its own properties. So it keeps its own identity, most of its own properties. So your example here, cereal and lemonade. Cereal, each piece of the cereal keeps its own properties. The salad that's shown, the lettuce keeps its own properties, the tomato keeps its own properties, whatever else is in there is going to keep their own properties. You can separate out mixtures. That's an easy way to tell. Some mixtures, like we discussed in the labs prior to this, are a little harder to distinguish, but they, as we start to talk about them more, talk about key words, you'll understand. Lemonade is a mixture because the lemonade dissolved in the water. So remember, I told you, anytime you have dissolving that happens, dissolving creates a mixture because you can get it back. And again, the components of a mixture can be present in any amount. So whereas your compound, you had to have a fixed amount. H2O had to have 2 parts hydrogen, 1 part oxygen. In a mixture, your salad, it doesn't matter how many pieces of lettuce, onions, tomatoes, cheese, whatever you put inside there. It doesn't matter how many. It's still a salad. All right, so when you're looking here, you can see that on the left, you've got elements. And if you look at what's going on here, there's nothing else inside of this. And that's why you can see the elements are the purest form of matter. Elements are made up of all atoms that are exactly alike. So there's nothing else in there. Compounds are also a pure substance. So you can look there at what's flowing around in the middle. And that would be like water molecules. If you were to pull out at any time one piece, it would always be a water molecule because there's nothing else in here. So elements and compounds are both pure substances. And they are identified as pure substances just because if you were to pull out a piece of either of those, you're always going to get the same thing. Nothing else is inside there. Whereas mixtures, you could see, you've got lots of different components. And none of them are chemically combined. They're just all flowing around in the same area together. So when you're looking at this, and what I would do is stop at this point and see if you can identify each of these types of matter and see which ones you think are elements, which ones are compounds, and which ones are mixtures. And then you can unpause after that because I'm getting ready to go over them. All right. So the cake, the first thing that we want to look at is that cake is made up of a multitude of things that are mixed together. Compounds are present in a fixed proportion. Cakes, you can have lemon cake, you can have chocolate cake, you can have all different kinds of cake, and it's still considered cake. So cake is a mixture. Okay. Gold. Gold is on the periodic table. Gold symbol is AU. So therefore gold is an element. Sulfuric acid is a substance that is made up of hydrogens, sulfurs, and oxygens. It is represented by the formula H2SO4. So since it's in a fixed proportion here, where you have 2 parts hydrogen, 1 sulfur, and 4 oxygen, then sulfuric acid is a compound. Milk is a mixture. Again, you can have skim milk, 1% milk, 2% milk, whole milk, chocolate milk, strawberry milk. You can vary the components and it's still considered milk. So one thing you want to look at, can you vary the components of this substance and it still be considered that same thing? And you can, so milk is a mixture. Plutonium is on the periodic table and its symbol is Pu. And so therefore it's an element. As long as you have a periodic table, it's pretty easy to identify your elements. Water is H2O, 2 parts hydrogen, 1 part oxygen. So this is a compound. Lemonade is a mixture because you could have strawberry lemonade. You could have lemonade that is very tart, lemonade that's very weak, but it's all considered lemonade because the components can be present in any amount and it still be considered lemonade. All right, the next one, lithium bromide, looks like this, LIBR. 1 part lithium, 1 part bromine, so therefore this is a compound, fixed proportion. The lithium, the amount of lithiums can't vary, the amount of bromines can't vary. The fact that those are the two, no other elements can be in there. So this is a compound, fixed proportion. Tin, also found on the periodic table, symbol is SN, so it is an element. Salt, as we went over with our labs, is sodium chloride, so NaCl. Therefore, this one is a compound. 1 part sodium, 1 part chlorine. Ammonia is also a compound. It's NH3. 1 part nitrogen, 3 parts hydrogen. So ammonia is a compound. Soda, as I explained to you guys with some of the situations on Wednesday that we read for the warm-up, soda is a mixture of water, the syrup, and carbon dioxide. Carbon dioxide is dissolved inside the water. Now you can have all kinds of different types, but they're all considered to be sodas. So you can vary the ingredients and it's still considered soda. Blood is also a mixture. Okay, you've got different, you got your red blood cells, white blood cells, platelets, iron, all of that flowing around. They're not chemically combined. They're present in different amounts. So you've got, and some people have elevated levels of white blood cells. Some people have elevated levels of your iron or decreased levels of your iron. So, and it's still considered to be blood. So that is a mixture. Carbon dioxide is made up of 1 part carbon, 2 parts oxygen. So that is a compound. Air is something people often mistake. Air is made up of 21% oxygen, about 75% nitrogen. Okay, so air, again, will have 21% oxygen, about 75% nitrogen, And then the rest is going to be carbon dioxide and some trace elements. None of them are chemically combined together. So your trace elements can be present in varying amounts. So air is a mixture of all those things together. And then dirt is a mixture. Depending on where you live, you're going to have mixtures of, like we have a lot of iron in our soil. You might go somewhere else where they have a lot of sand in their soil. So the ingredients being present in varying amounts means it's a mixture. If it is composed of specific amounts of different elements combined, then it's a compound. And if it's in its most basic form and can be found on the periodic table, then it is an element. Okay, we did a lot of this with the labs that we did the last couple of days, but looking at mixtures, mixtures can be separated back into original substances. Though sometimes it's a little hard to get them back, you can do it using their physical characteristics. So one example is evaporation, which I showed you in class. I actually sped up that by boiling off the water. When you had a salt water, I boiled off the water, and therefore you just had the salt left behind. Magnetism, you guys did that when you ran the magnet under. If you had a strong enough magnet, you could definitely separate the iron from the sand. Filtration, you guys did that when you separated the sand from the water. And filtration is just removing a solid substance or an insoluble substance from a solution. Chromatography is using the absorption rate of something in order to separate out like components of ink. And distillation is separation using of two liquids. If you have liquids combined together as a mixture, you can use their boiling points and boil out off the first liquid while leaving the remaining liquid behind, and that's how you can separate those. So looking more closely, when you separate mixtures, the different substances in the mixture are usually easily separated from one another for the most part, and the method you use always depends on which type of mixture you have. So once again, filtering, and you guys did this. This is good for separating an insoluble solid. So an insoluble solid is something that did not dissolve in the water. So if it didn't dissolve in the water, just like the sand is insoluble, the iron would have been insoluble. Anything that does not dissolve in the water, you can use a filtering technique to separate that from a liquid. So for example, sand can be separated from a mixture of sand and water using filtering. Evaporation, this is good for separating a soluble solid from a liquid. So this is like the salt water where, and I sped up the evaporation process by applying heat. But once you do that, the water will boil off at a certain temperature, salt's going to be left behind. And so therefore you've separated the salt from the water. Distillation, this is a distillation apparatus. And where you see the flame hitting the bottom of the Florence flask, that is a liquid. It's a mixture of two different liquids. At a certain temperature, let's say it's alcohol and water. At a certain temperature, like 70 degrees Celsius, your alcohol will start to boil off. Then it's going to come back down the condensing tube, which is right here. And when it comes back down that condensation tube, it's going to cool back down. So it goes from a liquid, which is right here. When it boils, it becomes a gas. Then it's going to come back down that condensation tube, turn right back into a liquid again. And what drops off here is going to be the alcohol. Okay, whereas this is the mixture of alcohol and water. You can't really see that. Sorry. Okay. So that's how you'll separate it out. And at about 100 degrees Celsius, a little bit before that, you would stop the boiling, separate this out, and therefore the water's left behind, the alcohol's in the separate container. All right, chromatography is a process used for separating mixtures by virtue of their absorbency. So if you put a black ink on a chromatography paper, you'll see the picture to the right shows how that could change into different colors as they absorb into the paper. So black ink is made up of a lot of different colors. So you would see the different colors that go into making up those inks. All right. Your different types of mixtures. Heterogeneous is a mixture that looks different throughout. The prefix hetero means different. So when you call it a heterogeneous mixture, it looks different throughout. You can see the pieces that make it up. So example, pizza, salad, chocolate chip cookies. You can see the individual parts that come together to make these mixtures. Homogeneous mixtures are the mixtures that you kind of confuse them to be compounds because you cannot see the individual pieces that make them up, like the milk here. The prefix homo means same. So a homogeneous mixture is a mixture that is blended so evenly throughout that it looks the same. So your examples here are milk, soda, and lemonade. All right, the definition of a solution is a type of a homogeneous mixture, is when you have one thing that's being dissolved inside another. And you guys keep in mind, when we've talked about dissolving, and we're talking about mixtures here, mixtures are formed by physical changes. So dissolving is a physical change. Keep that in mind because you can get the water back out and the lemonade and the sugar. Okay? A solution is made of two parts. First of all, you have the solvent, which is the substance that's doing the dissolving. So water is typically the universal solvent, which means it dissolves most substances. You have the solute, which is the substance being dissolved, like powdered drink mixes. So if you look at the picture over here, this is tea, and the water inside the tea is going to be your solvent. And let's say you put a cube of sugar in here. That sugar is the solute. The tea in here, that dissolved, is also a solute. So what is being dissolved inside a solution is the solute. What's doing the dissolving is the solvent. And solutions can be solids, liquids, and gases. Remember I told you that carbon dioxide is being dissolved inside the water for sodas. So you've got a gas being dissolved inside a liquid. All right, how much, and we're talking about solubility here, this is defined as how much solute can be dissolved in a given solvent. So if you increase the temperature of a solvent, then you increase the amount of solute that can be dissolved. So think about tea. If you have hot tea, it will dissolve more sugar than cold tea because the molecules are moving faster and they're going to mix those sugar molecules around a lot faster than if it's cold tea. The only exception are gas solutes like soda. If you increase the temperature, you decrease the solubility, and that's why soda can become flat in hot temperatures, because that increased temperature is going to cause that soda to not be able to dissolve or keep dissolved that carbon dioxide. So it becomes flat. So solubility is how much can a particular solvent dissolve when we're referring to solutes. All right, and if a substance can dissolve in a given material, it's said to be soluble. If it cannot dissolve in a given material, it's said to be insoluble.